Welcome back, everyone. In our previous lectures, we explored the vibrational motions of molecules and learned how these vibrations absorb energy in the infrared region. We also discussed how bond strength, atomic mass, and hybridization influence vibrational frequencies. But today, we are going to take a broader view. Instead of looking at vibrational transitions in isolation, we will examine what happens when vibrational motion interacts with electronic transitions. These interaction produces an important feature in molecular spectroscopy known as the vibrational core structure. Understanding this structure is essential when interpreting electronic absorption spectra, especially in UV visible spectroscopy. Let us explore how this works. When a molecule undergoes an electronic transition, an electron moves from one electronic energy level to another. At first glance, we might expect such a transition to produce a single spectrum line. However, when we examine experimental spectra, that is not what we observe. Instead of one sharp line, we typically see a band structure of multiple closely spaced peaks. This fine structure within the electronic band arises because vibrational transitions occur simultaneously with the electronic transition. In other words, when an electron jumps between electronic states, the molecule can also change its vibrational state. The result is a series of vibrational sublevel transitions embedded within the electronic band. These patterns of multiple lines inside an electronic transition is what we call vibrational core structure. In this analysis, we usually ignore rotational contributions for simplicity. That means we focus only on electronic energy plus vibrational energy. To describe quantitatively, we use an expression for the total energy of the molecule as shown in screen. The total energy can be written as presented here in the screen. Let us break this equation down carefully. The first term, epsilon EL, represents the electronic energy. This is the energy associated with the electron being an particular electronic state. For example, the ground electronic state or an excited electronic state. The next terms represent vibrational energy contributions. Here, nu is the vibrational quantum number. This quantum number can take values 0, 1, 2, 3, and so on. Each value corresponding to a different vibrational energy level. The symbol nu bar E represents the fundamental vibrational frequency of the molecule. This is the characteristic frequency associated with the vibration of a particular bond. The term Xe is called anharmonicity constant. This parameter describes how real molecular vibrations deviate from the ideal harmonic oscillator model. In a perfectly harmonic oscillator, vibrational energy levels would be equally spaced, but real molecules behave slightly differently. As the vibrational quantum numbers increases, the spacing between energy levels becomes smaller and smaller. This phenomena is called anharmonicity. This is an excellent moment to show What does this equation really tells us? It tells us that total molecular energy consists of two components, electronic energy plus vibrational energy. When an electronic transition occurs, the molecules may also change its vibrational state. Therefore, instead of observing a single transition, we observe many possible transitions between different vibrational levels. This produces the core structure in the electronic spectrum. Now, let us visualize these transitions using potential energy diagrams. On the screen, you can see two potential energy wells. The well on the first left represents the ground electronic state. The well on the right represents the excited electronic state. Within each well, you can see several horizontal lines. These lines represent vibrational energy levels. To distinguish between the two electronic states, we use a simple notation. Vibrational levels in the excited electronic state are labeled with single prime. We write them as a nu bar. Vibrational levels in the ground electronic state are labeled with double prime. We write them as nu double dash. Now observe something interesting. The vibrational levels in the excited electronic state appear closer together. What does this happen? Why does this happen? Because the answer lies in the bond strength. When a molecule absorbs energy and an electron moves into a higher orbital, the bonding situation often changes. In many cases, the bond order decreases. This means the bond becomes weaker and longer. A weaker bond corresponding to a shallower potential well. And when the potential well becomes wider, the spacing between vibrational levels becomes smaller. This is why the vibrational levels in the excited state appear closer together. Now let us consider the selection rules for these transitions. In pure vibrational spectroscopy, we usually apply the rule as delta nu is equal to plus minus 1. However, electronic transitions behave differently. When an electronic transitions occur, there is no strict restriction on the change in vibrational quantum number. In principle, transitions such as nu double prime is equal to 0 to nu prime is equal to 0, nu double dash is equal to 0 to nu dash is equal to 1, nu double dash is equal to 0 to nu dash is equal to 2, nu double dash is equal to 0 to nu dash is equal to 3 are possible. But even though these transitions are allowed, they are not equally probable. To understand which transitions are most likely, we must consider thermal population of the vibrational state. At room temperature, most molecules occupy the lowest vibrational level, which is nu double prime is equal to 0 or nu double dash is equal to 0. Higher vibrational levels contain very few molecules. Therefore, most electronic transitions originate from nu double prime is equal to 0 level. When we observe a sequence of transitions originating from the same lower state, we call this pattern a vibrational progression. For example, consider the following transition 0, 0, 1, 0, 2, 0, 3, 0. The notation here means nu prime and nu double prime. So 0, 0 means nu dash is equal to 0 and nu double dash is equal to 0. 1, 0 means nu dash is equal to 1 and nu double dash is equal to 0. 2, 0 means nu dash is equal to 2 and nu double dash is equal to 0. In this progression, the excited state quantum number increases sequentially while the lower state remains the same. This type of patterns is called nu dash progression. The exact position of each spectral line in this progression depends on several factors. This includes the electronic energy difference between states, the vibrational frequency of the molecule, the anharmonicity constant for both electronic states. All of these factors combine to determine the observed wave numbers in the spectrum. Understanding vibrational progression helps us to interpret complex electronic spectra. Instead of seeing the spectrum as a random collection of peaks, we can recognize structured patterns that reveal information about bond strength, molecular geometry, electronic state changes, and anharmonic vibrational behavior. Let us examine or let us summarize the key points from today's lecture. When molecules undergo electronic transitions, vibrational transitions often occur simultaneously. This produces a series of closely spaced spectral lines known as a vibrational core structure. The total molecular energy can be expressed as the sum of electronic energy and vibrational energy. Real molecular vibrations are anharmonic, which causes vibrational energy levels to converge at higher quantum numbers. In electronic spectra, vibrational levels in the excited state are often closer together because the bond becomes weaker. Most transitions originate from the lowest vibrational level, leading to a pattern called vibrational progression. By analyzing these vibrational progression, we gain deeper insight into molecular structure and electronic behavior. In our next lecture, we will learn how to organize these complex spectral lines using a powerful analytical method called Deslandres table. This method allows us systematically arrange vibrational transitions and extract important molecular constants from experimental spectra. Thank you for watching, and I will see you in the next lecture.